Hey everybody, my name is Chris. I'm a tutor here at Chegg.com, and I mostly do math and computer science. And in this video, I want to talk about finding powers and roots of complex numbers. So here we want to find the cube roots of the number I, or remember I is the imaginary unit, the square root of -1. So basically we want to solve the equation z cubed equals I. So we want to find all the complex numbers z that make this true. And because we have a 3 up here, we know that there are going to be 3 solutions. So how do we do this? Well, the very first thing that we do is take the right-hand side here and express it in polar form re to the I theta. Okay, so in order to find r and theta, we have to find the real and imaginary parts of this. So let's go ahead and write this a little more explicitly as z cubed equals 0 plus 1 times I. Okay, so that's just the same thing as I, but in a more expanded form. So this right here, that 0, that's our x, and the 1 right here, that's our y. Okay, so x is 0 and y is 1. So now we can find r and theta from there. So what we have is r equals the square root of x squared plus y squared, which is going to be the square root of, well, x is 0, so x squared is still 0. And then y is 1, so y squared is still 1. So we have the square root of 1, which is just 1. Okay, so that's nice. And what about theta? So theta, finding theta in general is a little more complicated, but actually because x is 0 and y is positive, then what that means is theta will always be pi over 2 in that case. So again, if x, the real part, is 0, and y, the imaginary part, is positive, then theta will be pi over 2. Okay, so that's actually pretty simple. It's just a matter of remembering that. So then re to the I theta, well, we just found out that r is 1 and theta is pi over 2. So then what we have, if we rewrite our equation using this polar form here, we have z cubed equals 1 times e to the I pi over 2. Okay, now how does that help us? Well, let's go ahead and move on to the second page here. So we have z cubed equals 1 times e to the I pi over 2. Now what I want to do is something that might seem a little strange, but I will explain it. So now I want to add plus 2n pi I, where n ranges from 0 to 2. Okay, now first of all, what are we doing here? So, well, first of all, let's answer the question, why does n go from 0 to 2? So here, we're solving the equation z to the third power equals all this stuff here. So because we have the 3 up here, that tells us that this n has to go from 0 to 2. So 0, 1, and 2, that's what n takes. N takes on those 3 values. Okay, now, well, the reason that we stop there is because once n hits 3, we're going to start repeating stuff that already happened, and we don't really want to repeat anything. We just want to find all the unique solutions to this equation here. So that's why we have n take on these 3 values, 0, 1, and 2. Now, why are we doing this at all? Why are we adding this 2n pi I? Is that even okay? Well, first let me come off to the side here and say e to the I pi over 2 plus 2n pi I. That's the same thing as e to the I pi over 2 times e to the 2n pi I. So that's just a property of exponents. Okay, that's a 2n pi I up here. And as long as n is any integer, positive, negative, or 0, then this whole thing is always going to be 1. Okay, this whole thing is always going to be 1, as long as n is any integer. So in particular, if n is 0, 1, or 2, then this whole expression right here will be 1, which means the whole thing will just equal e to the I pi over 2. So when we add this 2n pi I, we don't actually change anything. Then you might be asking yourself, well, why do we do that at all? Well, because our next step is to take the cube root of both sides. So when we take the cube root of both sides, we get z equals 1 times e to the I pi over 2 plus 2n pi I, this entire thing raised to the 1/3 power, where n still ranges from 0 to 1 to 2. Okay, so we want to find all 3 solutions of this equation, and unless we add this 2n pi I, we're going to miss them. So that's why we add this 2n pi I here, so that we are actually able to find all 3 solutions. So let's go ahead and simplify this a little more. So we're going to have z equals 1 to the 1/3 times e to the I pi over 2 plus 2n pi I, all of that divided by 3. Okay, so we can simplify that a little more. And then n ranges 0, 1 to 2. Okay, so let's go ahead and simplify this a little more here. Well, first of all, z equals 1 to the 1/3. 1 to the 1/3 is just 1, and then we're multiplying by all this stuff here. So let's simplify this exponent. So I times pi over 2 plus 2n pi I. For now, let's go ahead and just factor out the I. So what we have is pi over 2 plus 2n pi, that whole quantity, times I. Oops. So that's what we have for now. So this is e to the pi over 2 plus 2n pi all times I, and don't forget we are dividing by 3 because we took the cube root of both sides. Okay? Alright, so we have that so far, and still n is 0, 1, or 2. Now you might be asking yourself, well, how's this useful? What do we do next? Well, next, let's go ahead and go on to the next page. So just to recap real quick, we have z equals 1 times e to the pi over 2 plus 2n pi times I over 3, where n goes from 0 to 2, all the integers, 0, 1, and 2. So now all we have to do is plug in values of n, plug in these values of n and see what we get. So when n equals 0, we have z equals 1 times e to the pi over 2 plus 2 times 0 times pi, and then that whole expression multiplied by I over 3. So when we simplify, well, 2 times 0 times pi is all just 0, so there's nothing really happening up here. So we just have pi over 2 times I over 3, that's a 2, and then that is just pi over 6 times I. Okay, so this equals 1 times e to the pi I over 6. And then multiplying by 1 doesn't really do anything, so we can just say e to the pi I over 6. Now what if n is 1? Then what happens? So a little more complicated, but still the same idea. Just plug in n equals 1 and simplify. Then we have z equals 1, this 1 right here, times e to the pi over 2 plus 2 times 1 times pi, all multiplied by I over 3. Simplify that, and we're going to get pi over 2 plus 2 pi. So this 1 out here doesn't really do anything, so we'll just say e to the pi over 2 plus 2 pi, leave a little bit of space on purpose, and then times I over 3. Now we want to get a common denominator in there, so let's multiply this by 2 over 2. So we have pi over 2 plus 2 pi times 2 over 2. So that's going to give us, let's come off to the side and work on that a little bit, pi over 2 plus 4 pi over 2, which is 5 pi over 2. So we have e to the 5 pi over 2 multiplied by I over 3. So then what we end up with is e to the 5 pi and then I over 6. All right, and then finally, what if n is 2? N is 2, then we have z equals e. Let me use a different color. We have z equals e to the pi over 2 plus 2 times pi, all that multiplied by I over 3. So I'm running out of room a little bit, and because the idea is pretty much exactly the same as what we just did with n equals 1, I'll skip some steps and I'll say e, this equals e to the 4 pi, 8 pi over 2, 9 pi over 2 times I over 3. And then 3 goes into 9 3 times. So what we end up with is e to the 3 pi I over 2. Okay, so let's go ahead and go to page 4 and write all 3 of these out so we can recap. So we ended up with the 3 solutions, z equals e to the pi over 6 times I. We also had z equals e to the 5 pi I over 6. So let's say e to the 5 pi over 6 times I. And then we also had e to the 3 pi I over 2. So we'll say e to the 3 pi over 2 times I. Now, it might be okay for you to leave your answer in that form, but we could actually simplify a little more and write it out in a form that's more similar to this, in a rectangular form. So now what we want to do is use the theorem that says e to the I theta equals cosine of theta plus I sine of theta. So if we apply this 3 separate times to this, this, and then this, then what we're going to get is e to the pi over 6 times I. Well, let's just use this formula here with theta as pi over 6. Then what we get is cosine of pi over 6 plus I sine of pi over 6. And then from here, it's just a matter of knowing the unit circle. So let's see, cosine of pi over 6 is root 3 over 2. And then plus I sine of pi over 6, sine of pi over 6 is 1/2. So we have plus 1/2 I. Okay. So that's e to the pi over 6 times I. And then we have e to the 5 pi over 6 times I. So a different color. E to the 5 pi over 6 times I is cosine of 5 pi over 6 plus I times the sine of 5 pi over 6. And again, it's really just a matter of knowing the unit circle. So this is going to be negative root 3 over 2. And then sine of 5 pi over 6 is still positive 1/2, so this is plus 1/2 times I. And then finally, e to the 3 pi over 2, different color, times I. So e to the 3 pi over 2 times I. Using this formula again, we're going to have cosine of 3 pi over 2 plus I times the sine of 3 pi over 2. Now, the cosine of 3 pi over 2 is actually just 0, so we don't have any real part there, but the sine of 3 pi over 2 is -1, so this is just minus I. Okay, so that's actually pretty cool that we're actually able to write the cube roots of I in this nice form over here. Root 3 over 2 plus 1/2 I, negative root 3 over 2 plus 1/2 I, and negative I. Okay, so what's kind of interesting also is if we were to plot these points on the unit circle, so here we're talking about finding the cube roots of I, and when we converted to polar form, we found that R is 1, so we can try to plot these on a circle of radius 1, which would be the unit circle. So let's go ahead and do that and see what it looks like. It's kind of cool. So let's try and make this as circular as possible. Stretch it out a little more. I think that's okay there. All right, so probably as good as it's going to get. Now, what were our numbers again? Root 3 over 2 plus 1/2 I, negative root 3 over 2 plus 1/2 I, and negative I. But actually, it's going to be easier if we think about this in terms of thetas. So pi over 6, whoops, pi over 6, 5 pi over 6, and 3 pi over 2. So if we were to plot these points on the unit circle, root 3 over 2 plus 1/2 I would be right about here. Use a different color. Okay, so this is root 3 over 2, comma 1/2, or in terms of complex numbers, it's root 3 over 2 plus 1/2 I. And here, negative root 3 over 2 plus 1/2 I is going to be the mirror image of that point over the y-axis. So this is the y-axis here, x-axis over here. So this is negative root 3 over 2, comma 1/2. Or in terms of complex numbers, negative root 3 over 2 plus 1/2 I. And then finally we have negative I. And then negative I is the same thing as 0 minus 1 times I. Oops. Let's make that a little easier to read. 0 minus 1 times I. So that's going to be down here at the point 0 comma negative 1. Or in terms of complex numbers, that's 0 minus 1 times I, which is negative I. So let's erase this here. So we see that if we plot all three of our solutions here, they're actually equally spaced around the unit circle. So this is a unit circle here. We didn't label that, but we said it. So it's a circle with radius 1. Here's 1, -1, -1. Okay. So we see that the three cube roots of I are evenly spaced around the unit circle. So that's pretty cool. And this sort of thing will actually happen in general. Sometimes it might be harder to plot, harder to see what's actually happening, but in general, that's what will happen for equations of this form here. So that's pretty cool. So anyway, that's been an example of finding roots and powers of complex numbers. I hope you found this video useful, and thank you for watching.